Hello viewers, welcome to MTN Telescope. My names are Mr. Siwale Prince, and today we're going to revise Examination Council of Zambia past papers selected from some ECZ papers. I'm very much delighted that you have continued being part and supporting us so that this program continues to accelerate. So today, we'll start with a question that came in 2009, paper 2, chemistry 5070. And the question reads as follows. Question 1. The diagram below shows the properties and reaction of some substances. So there is a diagram there. We see green crystals being heated, forming colorless liquid F. We also observe there that to the same crystal E, there's addition of water forming a pale green solution. As you go to your right, you add acidified silver nitrate to form a white precipitate. Again, to the same pale green solution, we add green precipitate. We add few drops of aqueous sodium hydroxide to form green precipitate G. To green precipitate G, we add air to form a red-brown precipitate H. The question is, identify by name or by formula the green precipitate. But before we can do that, I would want us to quickly look at some of the concerned cations and anions that have been used on this question. To start with, let's just quickly look at under qualitative analysis. Under qualitative analysis, we have what are known as anions. We see in the diagram there that there's a formation of a white precipitate, white PPT. I have to bring to attention that to form a white PPT, there are only two cases there. The first case is when we're testing for a chloride and when we're also testing for a sulphate. These are the only cases where I've got a white PPT on the anions. So if we're testing for a chloride, what we add there is acidified silver nitrate to a given solution. And if we're testing for a sulphate, to a given solution, we have to add barium nitrate. Also, on the cation, we are told there that there is a green precipitate. So for green PPT, representing precipitate, the ions or the cation that gives us a green PPT, it is ion 2. Also, the ion that gives us a red-brown, red-brown PPT, the ion that gives us that is ion 3. So with this information, we can answer the question. So like we are able to see from the diagram, let me just take you back. We do observe that the pale green solution, we added silver nitrate, meaning that there was a formation of white PPT, and the ion there, it's a chloride. So we have the first part of the solution, which is a chloride. We also observe that there was a pale green solution. So for a green PPT, we know that there should have been ion 2. So from this, we do observe that the green crystal, it is that of iron chloride. So we're going to have iron chloride as our green crystal. Now, to this green crystal, after we add water, we form a pale green solution, which in this case is going to be iron chloride solution. So now, to iron chloride, I want us to add acidified silver nitrate. So this plus acidified silver nitrate, we're going to form silver chloride, which is in this case our white PPT, plus we're also going to form iron nitrate, iron 2 nitrate. Okay. Also, to this pale green solution, we've been told to add a few drops of aqueous sodium hydroxide. So we'll add sodium hydroxide. When that happens, we realize that there will be formation of iron 2 hydroxide. So there will be iron 2 hydroxide, solid, this which is a green PPT. Like we are told there, iron 2, it forms a green PPT. So we'll form iron 2 plus, we're also going to form sodium chloride as another reagent. So now, this is our green PPT. Also, we're told here further to say this iron 2 hydroxide, expose it to more air, it forms a red-brown PPT. The one that gives us a red-brown PPT in this case is iron 3. So I'm going to form iron 3 hydroxide. So now that we have identified the important reactions in this diagram, we're now going to look at the questions given forth. The first question is, identify by name or formula the green precipitate. So the green precipitate in this case, we can see it is iron 2 hydroxide. Remember, we can either identify by name or formula, so we can say iron 2 hydroxide. So this is the formula for the green precipitate. We can now move on to B. The white precipitate I. So the only white precipitate that we formed in this reaction was silver chloride. So the white precipitate is silver chloride. C, the red-brown precipitate H. So this one is the red PPT, iron 3 hydroxide. So the red-brown precipitate is iron 3 hydroxide. D, the colorless liquid F. So green crystals of E, after being heated gently, remember this salt contains water of crystallization. So if heated, the colorless liquid F that forms, which tains anhydrous copper 2 sulphate blue, is water, which is H2O. Oh. E. Name E. It is, the question is the green crystals E. So the green crystals in that case are the crystals of iron 2 chloride crystals. So these are the formula of the substances that have been identified in our diagram. Thank you very much, viewers. We continue our revision as we look at question 2. The question reads, ammonia is an essential industrial product which is manufactured by the Haber process. Give 2 reasons why ammonia is an essential. Why is this ammonia very important substance in industry? So there are many reasons why ammonia is important. Number 1, this ammonia, it is used in the manufacture of fertilizers, e.g. ammonium sulphate. Okay, so what happens is the ammonia, suppose I've got ammonia gas plus H2SO4, which is sulfuric acid. This forms ammonium sulphate. So this is one reason why ammonia is a very important ingredient. Apart from that, this ammonia, the main use of ammonia is that it is used in the Oswald process in the manufacture of nitric acid. So we can add to say it is used to manufacture nitric acid. Because of this purpose, this ammonia, you can also add to say it is used to make explosives such as TNT. TNT is just trinitrotoluene. Trinitrotoluene. Let's look at the second part of the question. Write the equation for the reaction in which ammonia is produced by the Haber process. Include state symbols. B. Remember, ammonia, it is made from nitrogen gas and hydrogen. So it is nitrogen plus hydrogen. And this reaction is reversible, forming ammonia, which is NH3 gas. 2 atoms of nitrogen, even this side there should be 2, so we put a 2 there. Adding a 2, it makes the hydrogen to be 6. To make these 6, we add the 3 there. So this is the balanced chemical equation for the reaction of nitrogen and hydrogen to form ammonia. But just a quick one. This reversible reaction here, it implies that ammonia breaks down at the same rate as it forms. So that's what this reversible reaction here indicates. So move on now to the second third part of the question, which is saying, which is C. State the conditions, sorry, I beg your pardon. State the raw materials from which the two reactants used to make ammonia are obtained. So the two reactants, we observe there that the first one is nitrogen. So nitrogen is obtained from, is obtained from air. So this nitrogen is obtained from air by fractional distillation. Of liquid air. So remember the question was just saying to tell us the source. So the source for nitrogen is air, then hydrogen. The source of hydrogen is obtained from natural gas, mainly which is methane. So that's where hydrogen is obtained. So it is obtained from natural gas, which is mainly made of methane. And what happens there is very simple. We react methane plus steam. This forms carbon monoxide gas plus hydrogen. Remember, this hydrogen form is not stable. So there will be further reaction of carbon monoxide plus more steam. Remember, steam is just water but G, producing carbon dioxide gas plus H2 gas. So this is how hydrogen is obtained from methane by steam reforming. So there the hydrogen is obtained from methane. Let's look at the other part of the question, which is D. State the conditions needed to obtain a satisfactory yield of ammonia by the Haber process. So the conditions: number one, we need a catalyst which is iron. So we need a catalyst ion. 2, we need a temperature of 450 degrees Celsius. 3, we need a pressure of 200 atm atmospheric pressure. So now, just a quick one on D. Here, I'll just comment on the temperature and pressure. On the temperature, I've said we need about 450 degrees Celsius. But it would be interesting for you to find out if the temperature is increased even more than 400, even above 500 degrees Celsius, the reaction is very fast. But that favors the reverse reaction, meaning that as the nitrogen is reacting to form ammonia, the ammonia, the rate at which it is breaking to give back nitrogen and hydrogen is enhanced as the temperature is increasing. Hence, to get a good yield, 450 is chosen as a compromise. Also, on the pressure, remember here we're using 200 atmospheric pressure, but a high pressure, it gives a very good yield of ammonia. However, it is very expensive to maintain. Hence, for economic purposes, 200 atmosphere is chosen. There was a French chemist who by the name of Henry Richard Terrier, he came up with the Richard Terrier's principle. He says that if the pressure is increased, equilibrium shifts where there are smaller number of moles and more ammonia is then produced. Viewers, let's move on to the last part of the question, which is now question E. Ammonia, the question reads, ammonia can be prepared in the laboratory by heating a mixture of sodium hydroxide and ammonium sulphate, as shown in the diagram below. Okay, you can see the diagram. There's a mix of sodium hydroxide and ammonium sulphate. They are being heated. And as you can see on your right-hand side, there's a drying agent there, which is calcium oxide. The first question is, write the equation for the reaction of calcium hydroxide with ammonium sulphate. The equation is going to be calcium hydroxide solid plus ammonium sulphate Akias, this is going to produce calcium sulphate solid plus ammonia is also going to be produced plus H2O liquid. So we can balance the equation there. Remember here I've got 2 nitrogen atoms. Even this side there should be 2. So we put a 2 here. Apart from that, we also know that the number of hydrogen atoms this side we've got 4 times 2, making them 8 plus 2, 10. But this side we just have 2 times 3, 6, meaning we're still remaining with 4 to be 10. So to make this to a 4, we add the 2 in front of water. So that makes our equation balanced. So when calcium hydroxide is reacted with ammonium sulphate, this is the correct chemical equation. 1 mark given for correct chemical formulas used, correct state symbols, and well balanced. The other part of the question is let's read the question. Describe a chemical test for ammonia. So what to do is just introduce damp lead litmus. Okay. To the gas, then the litmus paper turns blue. So this is the test for ammonia. Introduce damp litmus paper to the gas, the litmus paper turns blue. That is how we would identify that the gas produced is ammonia. Now, let's look at the last part of question 2 which reads, explain why concentrated sulfuric acid is not suitable for drying the ammonia gas. Remember, ammonia, it is alkaline. That's why it's been about 10 litmus paper to blue from red. So the reason why it is not used is simple. We're going to say ammonia is an alkaline. So if it is reacted, if sulfuric acid is used as a drying agent, so it can react with sulfuric acid. So what it does is, this ammonia, instead of drying the gas, this sulfuric acid, it does not dry the ammonia. Instead, it reacts with it, because ammonia is alkaline and the sulfuric acid is acidic. So there will be an acid-alkali reaction forming a salt, which would defeat our whole purpose of trying to obtain dry ammonia gas. The equation would be as follows. This would react to form ammonium sulfate. So that is why it is not used, because it reacts with the acid to form, the ammonia to form ammonium sulfate. Thank you very much, viewers. You're watching MTN Teleschool. Invite your family and friends, we revise together. We're now going to quickly look at the third part of the question, which is question 3. Okay, so question 3 is an energy level diagram. It reads, the diagram below is an energy level diagram for the combustion of gas propane in plenty supply of air. So that there's methane reacting with oxygen, burning completely, producing carbon dioxide and water there on the products. Use the above information to answer the following questions. Question 1. State the molar enthalpy change of combustion of propane. So just like you can see from the diagram, the molar enthalpy change is there where it's saying delta H, which is negative 2,220 kilojoules per mole. So that is the enthalpy change of combustion, A. So the enthalpy change is negative 220. Okay. Kilojoules per mole. B. What is X? So the X there, it is representing the energy of activation, or the activation energy. So X is the activation energy, which is the minimum amount of energy needed to start a chemical reaction. C. What is the purpose of Y? So there, that also represents the energy. So the purpose of Y is just to overcome the energy barrier So when the energy barrier is overcome, in order to start the reaction process. So that is the purpose of why. Viewers, thank you very much for watching. We're going to go into a very short break. As we come back, we're going to read some of your comments. And remember, you're watching MTN Teleschool. Invite your family and your friends. Thank you.
Rise up this morning, smile with the rising sun. Three little birds pitch by my doorstep, singing sweet songs, our melodies pure and true, saying, this is my message to you. Singing, don't worry about a thing, 'cause every little thing is gonna be alright. Singing, don't worry about a thing, 'cause every little thing is gonna be alright. Cause every little thing is gonna be alright.
How you use your data is up to you. With the widest network coverage, it's amazing what you can do on MTN.
This is my message to you.
Hello! This is all you need to know about data bundles. Like when you need airtime to make calls, you need data bundles to browse the internet, send and receive photos on Facebook, chat on WhatsApp, send emails, listen to music, and many other things. Data is measured in bytes, kilobytes, megabytes, and gigabytes. These are a bit like money, and just like your bank balance, your MTN account has a data balance that you can use to buy data bundles ranging from 5 megabytes to 20 gigabytes for daily, weekly, and monthly subscription. To buy a bundle, dial *335*1#.
From sending emails to browsing or watching online videos, many of the things you use depend on your device's functionality and network capability. Entry-level devices have limited data usage, whereas smartphones and computers have limitless data usage. The longer you spend online, the more data you use.
Sometimes you feel like your data is running out really fast. That's because today's modern technology and higher definition content require and use up a lot more data. No need to worry. Data can be managed to work for you by minimizing on the number of apps that automatically update themselves and turning off your data when not in use. Make sure you use data bundles to browse the internet. When your bundle is depleted, you will be billed from your airtime. Perform regular data balance inquiries by dialing *335*3#.
Thank you there, Miriam Samba, for the love. Okay, we can even see your comment there. I love my teaching subject. Please, let's continue the spirit. Okay. Okay, thank you very much, team, for your support. We now continue with our revision as we look at the last part of the question, which is question D of question 3. The question reads, how much heat energy is released to the surrounding when 2.2 grams of propane is burnt completely in oxygen? So to find the amount of heat energy, there are a lot of methods, but we're going to first use the simple one, which is we first have to find the number of moles of propane. So in this case, I've been given 2.2 grams of propane, which is C3H8. So let's first find the relative molecular mass for propane. So we have that This propane, it has got carbon and hydrogen. So there are 3 atoms of carbon, multiply times the mass number for carbon, which is 12. This gives us 3 times 12, it gives us 36. We also have 8 hydrogen atoms times 1, which gives us 8. Adding the 2, we get a summation of 44. So now that we know the relative molecular mass, we can easily find the moles. So the mole of propane is equal to mass over molar mass. So the mass in this case given is 2.2 grams divided by the molar mass, which is 44 grams per mole. Dividing 2.2 divided by 44, we get 0.05 mole. Now that we have the number of moles of propane that reacted, we can easily find the energy. Remember, our delta H for the reaction is equal to negative 2,220 kilojoules per mole, meaning that 1 mole gives us 2,220 kilojoules of energy from this. How about 0.05 mole? This will give us X. To find the value of X, you cross multiply. Don't put X, it means you have cancelled your work. Just cross multiply. CM cross multiply. This times that, we're going to have X mole is equal to 0.05 times 220. Kilojoules. So divide this by mole, even this one by mole. This mole and this mole divides, X is equal to mole, and this mole also divides. We remain with 0.05 times 2,220. This will give us X is equal to 111 kilojoules. So this is the amount of energy that was released to the surrounding by burning 2.2 grams of propane. We're done with the question. We can now look at the second question, which is question number 4. The question reads, there is an equation there. The equation above shows a redox reaction used to prepare chlorine gas in the laboratory. What is meant by the term redox? Just like the word red ox, this word redox, it carries with it 2 words. There's red and ox. This word red is from the word reduction, and ox is from the word oxidation. So a redox reaction is simply a reaction in which oxidation and reduction occur simultaneously. Yes, occurs simultaneously. Okay. So let's look at the second part of the question, which is B. The question reads, calculate the oxidation number of chlorine in HCl and explain why the change from HCl to CO2 is an oxidation process. So to do that, this one, the overall oxidation state, since there's no charge, it is equal to 0. So we're going to have that for hydrogen, the charge is positive. So we're going to have plus 1 plus for the chloride, which is X, giving us 0. So X is equal to minus 1. So this is the oxidation state of the chloride in HCl. Now, the question again is, why is the change from HCl to CO2 an oxidation process? We realize that in this HCl, the oxidation state of the chloride is minus 1. In this one, it is a gas. The oxidation state of chlorine, it is 0. So we see a change from negative 1 to 0. This is increase in oxidation state. So the reason why it is oxidation, because there's an increase in the oxidation state from negative 1 to 0. That's why this is an oxidation process. We can now move on to the next part of the question, which is C. The question reads, calculate the oxidation number of manganese in Km potassium manganate and manganese chloride. So we have in potassium manganate. So we want to find the oxidation state of manganese in this. For potassium, we know it is 1. So for manganese, we're going to say let it be X. And for potassium, we know its charge is positive 1. And for oxygen, since there are 4 of them, we're going to say 4 times the charge of oxygen, which is minus 2. This will also give us 0. So this will give us X plus 1. 4 times negative 2, it gives us minus 8, which is equal to 0. 1 minus 8, it is going to give us X minus 7 is equal to 0. So X is equal to plus 7. So the oxidation state of manganese in this case is equal to plus 7. Let's move on to calculating the oxidation state of manganese in manganese chloride. So using the same concept, manganese, it is going to be X plus, there are 2 chlorides. 2 chlorinates, so it will be 2 times the charge of a chloride, which is minus 1, giving us the overall charge in this case, which is 0. So we're going to have X, 2 times negative 1, it becomes minus 2, which is equal to 0. When we do that, we're going to have X, which is equal to plus 2. So the oxidation state of manganese in manganese chloride is equal to plus 2. So that is how we find the oxidation state. Without wasting much time, we're quickly going to look at the last question, which is question 5. The question reads, 10.0 grams of brass powder was added to excess dilute sulfuric acid, and all the zinc reacted with the acid, leaving a residue of copper. 1,200 cubic centimeters of hydrogen gas measured at RTP was produced in the reaction of zinc and hydrochloric acid. After crystallizing, the resulting zinc sulfate solution 10.76 grams of hydrated zinc sulfate crystals were obtained. The first question is, write a balanced chemical equation for the reaction of zinc powder with dilute sulfuric acid. Remember, zinc, it is a metal, so it is solid, plus the acid, which is H2SO4, sulfuric acid. When these two react, we produce a salt, which is zinc sulfate. Since what we are reacting with is just the metal, we're also going to produce a gas, which is hydrogen gas. So that is the balanced chemical equation for the reaction of zinc and sulfuric acid, which is, this one is self-balanced. Okay, let's look at the second part of the question. What mass of zinc was present in 10 grams of glass powder? For us to find the mass, we should first find the moles. But to have that, let's look at the data given. We've been given to say that hydrogen gas that was produced was 1,200 cubic centimeters. So with this, we can easily find the moles of hydrogen gas by using the formula mole. Okay, let me just take you back. In terms of volume, mole is equal to volume over molar volume. So this molar volume is 24 cubic decimeter at RTP. It is also 22.4 cubic decimeter at STP. So since it was at RTP, we're just interested in this. So mole, in this case, is going to be equal to volume over molar volume. So remember, the mole we're finding, it is the moles of hydrogen. So mole of hydrogen is equal to volume, which is 1,200 cubic centimeters divided by. Here, to simplify our work, we can convert this 24 cubic decimeter to cubic centimeters by multiplying that times 1,000. So we're going to have 24 times 1,000, which is 24,000 cubic centimeters per mole. We just multiplied 24 times 1,000 to change to cubic centimeter. So dividing that, we get 0.05 mole. So this mole, remember, it's for hydrogen. But we see from the equation, let's get back to the equation, the mole ratio of zinc to hydrogen, it is 1:1. So because the mole ratio is 1:1, it is the same. The moles of hydrogen and zinc will also be the same. So I'm going to have that mole of zinc is also equal to 0.05 mole because of the mole ratio of hydrogen to zinc, which is also 1 to 1. So if the mole ratio is the same, the moles will also be the same. Now that we know the moles of zinc, we can easily find the mass. Mass is equal to mole times molar mass. So the number of moles here, we have that it is 0.05 mole times the molar mass for zinc. If you check your periodic table, is it's 65 grams per mole. So zinc, it is 65 grams per mole. So multiply that times 65 grams. We're going to get the mass, which is 3.25 grams of zinc. That was the mass that was present for zinc. Let's look at C. C, it wants us to find out the percentage composition of mass of the blast sample. Before we can answer that question, let's find out also, what is this substance known as blast? Blast is a mixture of copper and zinc. So we're going to find the percentage composition of copper and that of zinc. But we already know that the mass for zinc, in this case, it is 3.25. So since blast is copper and zinc, it means the rest of the mass from the 10 is that of copper. So we're going to say mass of copper is equal to 10.00 grams for the sample of blast minus the mass of zinc, which is 3.25 grams. So we get there the mass of copper as 6.75. So now that you have the mass of copper and the mass of zinc, we can easily find the percentage composition. So A, the percent for copper is equal to mass of copper over mass of the blast sample. So the mass of copper in this case, it is 6.75 grams divided by 10.00 grams. Remember, we're finding the percentage composition, it is times 100%. So 6.5 divided by 10, it gives us 67.5. So this will give us 67.5%. So this is the percent for copper. Let's find also the percent for zinc, which is equal to mass of zinc over mass of blast. So the mass of zinc, we recognize that was 3.25 grams divided by 10.00 grams. So let's calculate 3.25 divided by 10.00 grams times 100%, which will give us 32.5%. So this is the mass of zinc in the brass sample. We can now look at the last part of the question, which is D. Calculate the percentage yield of zinc sulfate. To find the percentage yield of zinc sulfate, we first have to find what mass of zinc sulfate crystals were produced. To do that, we're first going to find the relative molecular mass of the zinc sulfate crystals. So let's find the relative molecular mass of Zn. So in this zinc sulfate, we have got zinc, sulfur, oxygen, and hydrogen. There's only one atom of zinc, so it will be 1 times 65, giving us 65. Sulfur, there's also 1 times the mass number, which is 32, giving us 32. Oxygen, there are 4 plus these 6 this side, making them 10 times 16, giving us 160. Hydrogen, it would be 6 times 2, which is 12. So it would be 12 times the molar mass, which is 1, giving us 12. So we're going to add so we get a total of 269 as the molar mass for the zinc sulfate crystals. Now, remember also, let me just take you back. We recognize here that, again, the acid and the salt that is produced, the mole ratio also here, it is 1 to 1. So if the mole ratio is the same or 1 to 1, the number of moles will still be the same. So we're still going to use 0.5. So I'm going to say mole of zinc sulfate crystals is also equal to 0.05 mole, because the mole ratio of the reacting species is the same. Now that we have the moles and the molar mass, we can easily find the mass. So mass is equal to mole times molar mass. The mole in this case is 0.05 mole times the molar mass, which is 269. Okay. Grams per mole. So I'm going to have that the mass of the crystal is going to be 13.45 grams. So this is the mass that will be produced. Now that we have the mass, we can easily answer the question, which is find the percentage yield. So percent yield is equal to actual yield over theoretical yield. Remember, the theoretical yield is this mass we have calculated, and the actual yield is given. So the actual yield in this case was given as 10.76 grams down the question, divided by the theoretical yield, which is 13.45. Grams times 100%. So the percentage yield is going to be 10.76 divided by the answer, it is going to be 80.2%. So that is how we find the percentage yield for the formation of, the percentage yield of the zinc sulfate crystals that were obtained. Thank you very much, viewers, for watching. Please remember to like our Facebook page, MTN Zambia. As we continue with this revision program, invite your friends and family. Thank you very much for watching. Stay tuned.
Tiende pamoja ni mtima umo. 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 Tiende pamoja